Hello fellow problem solvers. So they're going to be doing a problem from the Asian Pacific Math Olympiad 2004, problem number 4. So first let me make clear what the problem is. This is the whole part of a number, of this number, which I'll call x. The whole part of x is called the greatest integer, not a positive integer, in this case it's going to be positive, but the greatest integer that is not bigger than x. That's what the whole part of x is. And we must, so basically if you have like a 2.5, the whole part of this is 2. Right, so that's the idea. And we must show that this whole part of this number is always going to be even for every n that's a natural number. Now I suggest you try this problem out for a minimum of 30 minutes, ideally an hour to an hour and a half, especially if you want to get better at number theory and you think you're like good, you want to get to the next level. This is a cool problem to spend your time on. At most though, 3 hours, I wouldn't go more than that. So now without further ado, let's begin. We need to show that 2 divides this. So n times n plus 1 over like n minus 1 factorial over n times n plus 1. So now when we have a factorial, here, when is this thing not an integer? And the answer is it's not an integer in a few cases, really a few cases, because say if both n and n plus 1 are not prime, so they're composites. Say n is equal to a times b, n plus 1 is equal to c times d, such that all of a, b, c, d are greater than 1. Then we have that and say that a is also greater than or equal to b, c greater than or equal to d. Then we have that inside in the first n minus 1 integers. First of all, a, b, c, d are all, a is relatively prime to c, and relatively prime to d, b relatively prime to c, b relatively prime to d. That's the first thing. These numbers are relatively prime, and we'll have that, which means also they're different. That's the important part. And so we'll have that a, b, c, d will show up in the first n minus 1 integers, and ergo will be a part of this. And then we'll have another even number to make this whole thing even. Right? So that's sort of a general overview of how this thing will work if n is, if n is composite. If one of these is a square, and there's a little bit more analysis to be done. If say a is equal to b, then both a and 2a will show up here, and they're different from c and d. That's basically the idea. So maybe now we can write this down. Like we could write this down in words. Pretty much, I think only need to pay attention to the case if n is equal to 4, or maybe I think n is equal to 4 is where we have to pay attention. Basically the first couple of cases where we're not sure if like 2n plus 1, because now what? A is less than the square root of n, less than or equal to the square root of n. Actually, b is less than or equal to the square root of n. Now to make sure that 2b shows up, we need this. This is less than or equal to the square root of 2n. We need to have that n minus 1 is greater than or equal to this. That's basically the only thing we need to have. And for say 4, this isn't true. But then for 6, this is 2 times the square root of 6. The square root of 6 is around 5. Again, this is not true for 6. But we don't have that problem for 6. So maybe just like a couple of cases we would need to like do by hand here. But after that, after we've done those cases by hand, the big issue where this is not an integer is where n is a prime, or when n plus 1 is a prime number. And we will have to deal with those. So now first let's deal with the cases when n is like 1 through 6. So this is what we have for those first couple of cases. And if you now don't have an idea, how do I deal with p, when n is p and n plus 1 is p, you might go like, I don't know how to deal with that. Well, this work we've done here, we've also taken a look at n is 6. That's what n plus 1 is a prime, and we got 20 over 7. That's 1 less than 21. And here we got a 90 over 7. That's 1 less than 91, which is 7 times 13. So maybe there's some hint there. Are we going to be 1 away from 1? Maybe. It's important to notice these patterns, and then you make a potential hypothesis. Would I make this hypothesis if I didn't see this problem before? I don't know. But it's important to keep making these and then testing them out. That's where the creativity in these problems comes in. So now we need to clear this up and look at those two cases. So the first case, let's do the case when n is equal to a prime. Right. Then we have p minus 1 factorial over there over p times p plus 1. Now my question to you is, what is this thing equal to? The answer is we don't know. Now we can we can have guesses, like for example here n was 7 and this was 13, like 1 away from 13 times 7. Like this up here, actually not up here, like this whole thing was 1 away from 13. Though 13 times 8 is what? That's going to give us 91 plus 13, 104. What is that close to, for example? That could be a question we might ask ourselves. And it's close to something. So we have, this is going to be an integer, and we're curious what will happen when we divide by p. Now, what do we use? Well, we need to evaluate somehow p minus 1 factorial over this with respect to p. How far away from p is it? And what we do is we say, well, we know that p minus 1 factorial is congruent to minus 1 modulo p by Wilson's theorem. Now here, what can we say? Well, this is minus 1. So if I add a 1 to it, it will be congruent to, this will be divisible by p. But I don't really have this. I am dividing p by this over p plus 1. So the question is, what happens when I divide by p plus 1? And here's where I invite you to pause for the next 5-10 minutes and see what happens. And the answer is, well, wait. P plus 1 is going to be, so let's say, is p plus 1 a square? If it's a square, then it's x minus 1 times x plus 1 is equal to p. That means this is 1, this is p, because it's two things multiplied together gives you a prime, which means that x is 2, p is 3. We don't have that case, n is greater than 3. So we're not dealing with this. So it's going to be some a times b, where a and b are different. This p plus 1. And now we know that a times b is in here, right? So we're looking at p minus 1 factorial over a times b. We're looking at what this is congruent to modulo p. There are many ways to go about this. One way is to say, well, if I'm taking out two numbers, when you multiply them, a number, a and b, when I multiply them together, I get a number which is 1 modulo p. All right, I get a times b is congruent to 1 modulo p. So when I leave them out, I'll get as if I divided by 1. Now, if you're not comfortable doing that, there's still another way to do this. Let this be congruent to k modulo p, and we're trying to figure out what k is. Multiply both sides by a and b, and we get that p minus 1 factorial is congruent to kab, which is congruent to k modulo p. However, we know this is minus 1 modulo p, so k is congruent to minus 1 modulo p. And now what does that tell us? It tells us that this plus 1 is divisible by p. So we have now p divides p minus 1 factorial over p plus 1 plus 1. Right, so k plus 1, that is this, is going to be divisible by p. And now, what does this tell us about the integer part of this number? Here's where I invite you to pause for the next 5 to 10 minutes and think about what does that tell you about this. And here is the solution. So it tells us that, so p divides, when I have p minus 1 factorial over p plus 1 plus 1. So when I add something extra here, something very little extra, I'll get a whole integer. So I have this whole thing is an integer. It's a positive integer. Now this is just a bit bigger than this thing right here. In fact, it's bigger for how much? How much bigger is it? It's like I added 1 over p to this number and I got a positive integer. So I have this number which is x plus 1 over p. If this is x, this is an integer, right? So if this integer is odd, then I know that the whole part of x is going to be even, because these are like evens and odds are consecutive one after another. And in fact, it has to be odd for x to be even. So what do I have now? I need to show then that this here is odd. I know it's an integer, I need to show it's an odd. How will I do that? Well, pause for a few minutes, ask yourself, how do you do that? And the answer is, well, this thing here is pretty even. It's very, very much so even. Why? Because even if p plus 1 is a power of 2, I'll still have many powers of 2 in p minus 1 factorial, much, much more. You can calculate this, you can look at, say, if p minus 1 was 2 to the alpha, then p plus 1 over 2 would be in here, and what would else be in here? P plus 1 over 4 would be in here. And if alpha is at least 3, right, I'm done. And I've also actually looked at the case p is equal to 7, so alpha would need to be at least 4. And now it's 4 because 15 isn't prime, so it would need to be at least 6, right? No, it would need to be at least 5 because 31 is a prime number, right? So it's at p31 is when we would have maybe a little bit of an edge case, but not really. And we would have enough even numbers here. And if p plus 1 isn't the power of 2, then the highest power of 2, then p plus 1 is between 2 consecutive powers of 2. That consecutive power of 2 is in here. The smaller one is in here, and p plus 1 doesn't have more 2's than that. So this is even, so this plus 1 is odd, over p is an integer. So we have this thing right here needs to be, and what? A even integer. So now this is the case when n is equal to p. If you didn't solve this, I really urge you to pause and try to solve the other case n plus 1 is equal to p for the next 15 minutes. And here's that solution. So we have n plus 1 is equal to p, or in other words, we have n minus 1 is equal to p minus 2. So now we have p minus 2 factorial over p minus 1 times b, right? This is the number we're looking at. And you're like, oh, but that previous case was easier because you could use Wilson's theorem right away. Now, how can I use Wilson here? There's no Wilson. Where's Wilson? And the answer is, wait a second. What do we know? You mentioned this guy Wilson, right? So p minus 1 factorial is congruent to minus 1 modulo p, right? You're calling this guy, right? So this over this, what is that? It's as if I divided this by p minus 1 squared, right? So is p minus 1 squared, or in other words, is p minus 1 in p minus 2 factorial? And the answer is yeah, it's in here. It's very likely in here. This is not a prime, so is p minus 1 a square? P minus 1 is a square. Oh, what do we do then? Well, then x and 2x are both in p minus 2 factorial. And so we're good even if p minus 1 is a square in that case. And we are good because 2x is less than, what's it called? Less than or equal to p minus 2. And how do we know this? Well, from here, we know that x squared plus 1 is equal to p. This is greater than x squared, so the square root of p is greater than x. And so 2x is less than 2 square roots of p, which is less than or equal to p minus 2. For pretty much, this is the square root of p minus 1 squared, and then minus 3 greater than or equal to 0. Like this is true if and only if this is true. And this is true pretty much for every prime p, right? So actually not for every prime p. Let's be very, very careful. So the square root of p needs to be what? Well, actually, we might need to have a couple of cases to deal with. So it's good to be cautious. I need this in here. What do I need? I need 3 less than or equal to the square root of this. So I need the square root of p be greater than or equal to the square root of the square root of 3 plus 1 needs to be less than or equal to this. And now I need p to be what? This is p greater than or equal to 3 plus 1 plus 2 square roots of 3. P minus 4 greater than or equal to 2 square roots of p. 2 square roots of 3, 2 square roots of 3. Is that less than a 4? Yes, it's less than 4, so I need to have p minus 4 greater than or equal to 4. I need p to be greater than or equal to 8, right? And I think I've done the case if n minus 1. So I just need to do the case n is equal to 8 by hand. No, actually, no, this is n plus 1, my bad. So n plus 1 is n plus 1 of prime. I've done all those cases, right? For n is equal to 6, already captured that. So now we're in the clear with regards to like this over this being an integer. And now let's look what it's actually congruent to. So we have that, let's say p minus 2 is, what's it called? So we're dividing by p minus 1. So p minus 1 is equal to some a times b. And this is congruent to minus 1 modulo p. So now say p minus 1 factorial over p minus 1 squared. Let this be congruent to k. Multiply everything through by p minus 1 squared, and we'll get that this is modulo p, and you get p minus 1 factorial is going to be congruent to, so p minus 1 squared is going to be congruent to 1. This is congruent to k, and this thing on the other hand is congruent to minus 1 modulo p. K is congruent to minus 1 modulo p. So this thing right here is congruent to minus 1 modulo p, which means p divides p minus 2 factorial over p minus 1 plus 1. And now the same deal as before, we have that if p, we have p minus 2 factorial over p minus 1 plus 1 is an integer. And this is the integer that's going to be greater than our x. Like this is going to be that odd integer. We've added 1 over p, same argument as before. Now, is this up here going to be odd? Well, is this going to be even? And the answer is this is going to be even by the same argument we had before, right? This is going to have as many 2's as we need. And this finishes up our problem. This is how we show this. It's a very cool problem where you get to sort of see, okay, I need this. What is this? What do I need? And then you're like, oh no, what am I going to do when I have p? And then you realize, wait, I can actually, let me see what integers close by. Let me take advantage of Wilson's theorem, right? And then you can say, okay, I know sort of where this is. And this solves our problem. And as always, thanks for problem solving.